Hello, my name is Patricia Gillis. I'm going to talk today about a study that looked at the relative toxicity of road salt alternatives to freshwater mussels. I'd like to acknowledge my co-authors, Joseph Salerno, Jim Bennett, Irina Kudla, and Margot Smith. We are at Environment and Climate Change Canada and Fisheries and Oceans Canada. Over the past number of decades, the amount of road salt that is used in North American roads has increased significantly, and along with this we've seen a steady increase in the concentration of chloride in surface waters, both in urban and often now in non-urban areas. There have been negative impacts of freshwater salinization demonstrated across a range of freshwater organisms. Freshwater mussels have a heightened sensitivity to salt, and in fact when compared to the sensitivity of other freshwater biota in the species sensitivity distribution, you see that Glaucidia fall out at the bottom, which means they are the most sensitive species to salt. Road salt usage in Canada is shown on the graph on the map on the left. The intensity of the red color is how much road salt is used in that area. The map on the right is the freshwater mussel distribution in Canada, and the darker red color indicates that in this area there are more freshwater mussel species. And as you can see in southern Ontario, where there is a lot of road salt used, 41 of Canada's 55 freshwater mussel species are located, and this indicates that freshwater mussels are at risk of road salt-induced freshwater salinization. To determine how road runoff affects freshwater mussels, we collected road runoff and melt samples during a winter melt as that samples were about to enter a freshwater mussel habitat, including species at risk in this area. The samples that were collected were used in exposures with juveniles and Glaucidia, and we found that a serial dilution of winter road runoff was acutely toxic to Glaucidia, as well as juvenile mussels. This graph shows that viability, the ability to close valves, decreases as they are increased to more winter runoff. When we looked in the receiving environment where this bridge drains into the mussel habitat, we found fewer mussels immediately surrounding the bridge. Now there are other possible contributing factors that could be occurring here, but this is the first indication that freshwater mussel wild populations can be impacted by winter road runoff. The negative impact of road salt-induced freshwater salinization has led to an increase in de-icing alternatives. In fact, in 7 Canadian provinces and many American states, these are already being used. Salt-sensitive biota, including freshwater mussels, would be expected to benefit from a transition to alternatives. Liquid road salt alternatives have a more targeted application. As you can see, these stripes on the road here in the lower photograph are a liquid de-icer being applied, and because it's directly applied to the surface and not bouncing off into the ditch, less salt is applied. Some alternatives are based on fermented agricultural products, including beet juice, and these products are marketed as eco-friendly. Here's a customer testimonial from a beet juice containing product. Being made of beets, it supports both farmers and is truly non-harmful to the environment and will not freeze. Supporting farmers is what we are all about. If you're starving, you could even eat it. Now, even though I may have put this here as a bit of tongue-in-cheek, even though it's marketed as an eco-friendly product, we still need to understand how it can impact the environment. All de-icing products have the potential to run off into aquatic environments. However, the effect of those used for alternative de-icing applications on biota is not well understood. So to investigate this, we obtained 3 products: de-icing brine, a brine beet juice product, and a product that was just beet juice. We extracted Glaucidia from gravid females and exposed them to dilutions of these 3 products. At the end of 24 and 48 hours of exposure, the ability of the Glaucidia to close their valves was assessed in order to derive an effect concentration. An EC50 is a concentration that affects 50% of the exposed organisms, and the effect for toxicity noted here is their ability to close valves and complete their life cycle. Here are the data from the exposures with the three products. Along the x-axis is increasing concentrations of de-icing product, and along the y-axis is Glaucidia viability. All three products were toxic to Glaucidia, with increasing exposure to them. However, the beet juice products, beet juice brine and beet juice alone, were 10 times more toxic than the brine. The EC50s are 0.42 for brine, 0.03 for beet juice, and 0.02 for brine beet juice, and 0.02 for beet juice. In order to determine what was causing the toxicity of these products, we characterized the exposure solutions. The brine exposure solution contains sodium, chloride, and numerous trace metals. The beet juice containing exposures contain trace metals as well, major ions, and sugars. We observed poor water quality in the 1 and 2% beet juice exposures. These are the areas where we noticed toxicity was well below the 1 and 2% exposures. So even though there's a fair amount of trace metals, some that reach toxic levels in the 1 and 2% exposure, and this is where we noted decreased water quality, Glaucidia were dead long before we reached these levels. Looking at the major ions in the solutions, the de-icing brine, the orange line shown here is the increased concentration of chloride as the viability of the organisms decreases. In the de-icing brine, chloride is thought to be responsible for the observed toxicity. In the beet juice brine, we have both potassium and chloride, and both increase as the concentration of the product increases. But it is the potassium, which is shown in green here, and the potassium EC50 is shown in the dashed line. It's the potassium in the brine beet juice and the beet juice alone exposure that correspond with the observed toxicity, indicating that potassium appears to be driving the toxicity in the beet juice exposures. Hazard for these products was determined taking into account their application rate. These are the application rates for the various products obtained from the industry. These are the EC50s observed in these exposures. And this is how many times the EC50 there is in each application of the various products. So relative to brine, these are the relative hazards. When shown in here, we see brine is a much smaller proportion of the hazard. Brine beet juice, 13 times the hazard of brine, and beet juice is 19 times the hazard of brine, the most hazardous product based on the observed toxicity. All three of the products tested in this study were alternatives to road salt. So to compare the hazard of road salt versus the alternative de-icing products, we estimated hazard based on the concentration of chloride and or potassium that are in the product and can enter the aquatic habitat per application, as well as the toxicity, the known toxicity of chloride and potassium to Glaucidia. This time, hazard is expressed relative to traditional road salt. Here's the relative hazard. Gray is the road salt. Once again, you can see that compared to the other products, brine is the least hazardous. Brine beet juice is a similar hazard to mussels based on application rates and known toxicity of the ions, but beet juice is the most hazardous product of all when comparing the various de-icers to freshwater mussel early life stages. Freshwater mussels are very sensitive to potassium. These two graphs are a compilation of the acute toxicity data of freshwater biota. Shown here in red are the most sensitive organisms, and 5 of the 6 most sensitive organisms are freshwater mussels in the acute dataset. Similarly, in the chronic dataset, the 2 sensitive organisms are freshwater mussels, indicating, similar to chloride, that freshwater mussels are among the most sensitive organisms to potassium. Looking at potassium in the environment, compiling 10 years of potassium data from long-term water quality monitoring sites with over 1,600 readings per year, we see that mean potassium concentrations range between 2 and 3 milligrams of potassium per liter. But yearly maximums range from 40 to 105 milligrams of potassium per liter. The red area in this graph is all the samples that would have exceeded the EC50 for potassium for freshwater mussels. Potassium has long been thought to contribute to the distribution of freshwater mussels. In 1973, Emily conducted a study where it looked at the levels of potassium in the habitat and mussel populations. The green areas shown here are areas where potassium is under 4 milligram per liter and where habitats that did support mussels. The red and the orange areas were marginal or no clams, and this is where potassium was exceeding 4 milligram per liter. So what potassium regulations are there out there to protect mussels? Well, not very many. In Europe, the REACH documents show that a no-effect concentration of 0.05 milligram of potassium per liter, and in EPA Region 3, there's a chronic benchmark of 53 milligrams of potassium per liter. If we have a widespread movement from traditional de-icing products based on sodium chloride or just road salt, and we move to these agricultural-based products, these data raise the question, how will an additional influx of potassium affect mussels and other potassium-sensitive organisms? So to conclude, liquid de-icing products are toxic to Glaucidia. Beet juice containing products were 10 times more toxic than a salt brine. And based on the application rates and observed toxicity of the liquid de-icers that we tested, beet juice containing products pose 13 to 19-fold higher hazard to mussels. Compared to traditional road salt, and taking into consideration the amount of chloride and/or potassium that could enter the aquatic environment per application and the known toxicity of those ions, beet juice was still the most hazardous product, followed by road salt, brine beet juice, and finally salt brine. Potassium in some surface waters in Ontario exceeds the level known to cause toxicity to Glaucidia in the lab, and the level suspected to influence mussel distribution, but very few water quality regulations for potassium exist. Further study is needed to understand how potassium affects freshwater mussels, and whether a shift to eco-friendly de-icing products affects potassium levels in surface waters, and ultimately how does this affect potassium-sensitive organisms, including mussels. A number of people provided significant input and value contributions to this product. They are listed here, and I'd like to acknowledge and to thank them for that. I'd like to thank you for tuning in and checking out this presentation. During the breakout session on April 14th, feel free to ask a question, or I can be reached at my email shown here. Thank you.